DC bearing is a small program to determine the bearing capacity, just only the bearing capacity of a foundation. Yeah, it just includes that. DC footing instead includes all foundation verifications like overturning, equilibrium, sliding stability, and the bearing capacity, and the design of the foundation. And we don't have this all in this program, just bearing capacity. Yeah, when we start DC bearing and when we create a new project, then we already have one foundation with one soil layer here and a flat surface. Then I want to show you the analysis standards. It's the same as in the other programs. You can choose between the EU code and other national standards like the DIN 4017 or like the for Switzerland, Austria, or you can also choose that it calculates with the methods by Terzaghi and Brinch Hansen. And if we select Eurocode, we have national settings here: Germany, Austria, France, UK, Italy, and Spain. And there's the opportunity to set free like other standards if it's like, yeah, if you want to add any other national settings, then we send OK, and then we can see here the predefined values from the chosen standard, and this cannot be changed manually. If you want to have any other values, you must yeah, use the free buttons here. Then we can also set the earth, like the standard for the earth pressure. We have the DIN 4085 standardly in the program. Yeah, we mainly use it in Germany, so yeah, but you're welcome always to choose any other standard then which you need for your country. Yeah, we are done here. We enter name. And yes, we have 3 different foundation types. So we click on the foundation and this window opens then. Then we have a rectangle foundation, like with the dimensions A, B, and H. Then we have a strip foundation with like an endless A, like kind of endless A, and the width B and the height H, or we have a circular foundation as a third opportunity. But we want to show you the verification for rectangle foundation with the bottom edge at -1. The width in both directions with 3 meters, a height of 1 meter. So the top of the foundation is at the same level as the surface, like the yeah, the terrain surface. Then we want to have a bottom inclination alpha, which is here with 5 degrees, and the unit weight with 25 kilonewton per meter. Yeah. Then we can have like a bottom plate or a support, but this is only shown in the graph. It has no influence for the verification. Yeah, like the verification is like dependent on the load, the soil, embedment in the soil, and the slope on the surface top. Yeah, but we offer that there's like the opportunity that we can have that we can calculate the bearing capacity for different widths or like different depths. So that the program, like we have a table of like, for example, when we say we want to see the utilization factor for width from 1.5 meters to 4 meters, with a data width of 0.25 meters. Then it gives a table in the output that we can see where the utilization factor is close to 1 at a certain depth or like a certain width. Now you can say here the depth, but we just have the width here now, and we want to keep the aspect ratio that it stays a square. Yeah, so we can see our foundation with the width and the bottom inclination. The next one is that we enter the soil parameters. We can have multiple horizontal layers in DC bearing in any depth we want. And the first layer is already shown. We want to adapt it, so we double click on it. And the first layer, we want to have a loose sand. You can either enter the soil parameters in here, or we can use the parameter suggestions. We also do upload this in the other programs, so you might have seen this before. We choose the loose sand in here, and we say apply. You can also like enter here like different soil types if you want. Like you can change those parameters and save them, or you can delete it. So you can have like different, like when you have like a soil which is like you use permanently, you can add this in the parameter suggestions. Yeah, you can apply this, say okay, and then you can see the sand in an orange color. And like if the soil type is known in the program, like the sand here in this case, the soil layer is shown in a specific color. Sand is orange, because like all soil types are associated to a specific color in the symbol editor. And you can find the symbol editor here in the settings. So we have each, we have many soils. And if the program recognizes like the short or like the sand, like the long name, then it fills out the color of the soil layer. So you can see here sand is orange. Say close. You can edit the existing soil types, or you can create new ones. So we say close. And with this icon layers, we can add more horizontal layers. So we want to have a second layer, which is like silt. We can use the parameter suggestions. We have a slightly plastic silt in here and apply at the bottom depth to depth top edge at 1.5 meters. Apply, okay. And then we have at 2 meters, we want to have our middle dense gravel. Apply, okay. So we have 3 layers now. And we can also add slopes and excavation stages at the surface. So we can define different stages with different abutments of the foundation. And you can also define a groundwater level, which is always associated to an excavation stage, since it can change from stage to stage. Yeah, so if you just want to have define a groundwater without any excavation stage, we must at least define 1 excavation stage at the top surface. And we want to have a little excavation with a little slope. So we use this icon here, excavation, and the slope will start here and goes to here. Then this window opens. We must enter a name. Then we say the excavation depth is 0, so it starts at the surface. Then we have a slope here, and which is the data here. And then we want to add the groundwater level, which is at 1.25. You can also apply an imposed load in the pit base, which is like has a positive influence for the verification. And you can also predefine the coefficients for the analysis. Like it's actually calculated automatically, but you can predefine it. And if you want to do that, you can do this. Like you can enter the values here. Yeah, then we have the earth pressure type here. So like if the foundation embedment is almost the same at both sides, like left and right side, and the surface level is almost at the same height, yeah, then we can use the earth pressure at rest. And if not, like and the excavation is quite deep at one side of the foundation, then can use the active and passive earth pressure. And the earth pressure can just be as high as much the load can activate. So like it's not part, like it won't happen that the passive earth pressure would press the foundation against the load side. So yeah. Yeah, so we're done here with the excavation, and you can see the slope here and the groundwater level. And we also want to add a slope at the other side. Is this icon here. We want to have a slope here, and we can see that. Yeah. So we're done with the soil here, and the ground failure feature, which will go, I think, like the most unfavorable direction is like in this direction then with the excavation stage. It will go through all 3 layers. And according to the DIN 4017, Phi and C must be averaged, but it is only permitted when the difference is less than 5 degrees. Yeah, but there's no procedure when the difference is greater. So we use an improved procedure according to Schulze, published in the German Grundbau-Taschenbuch. Schulze recommends to weight the values by the vertical soil load in addition. So like in this way, the values in a graded depth with like higher soil load have a large influence on the verification. And yeah, like and with this method, it's possible to weight the values like with any values of Phi, C, and gamma, like also when the values have like a greater difference, like with more than 5 degrees. Okay, we want to center this. Yeah, then we want to apply the loads. We have one load case, one, with a dead load, and in the design situation permanent. And the program does not combine, sorry, does not combine all the load cases. So it has no load case combination. So if you want to have the same like loads combined with each other, it must always be in one load case. So like the verification is separated in like for each load case and excavation stage. Yeah, so we have the load. We have a vertical load of 1000 kilonewton, then a horizontal load in X direction with minus 50 degrees, 50 kilonewton, sorry, which shows then in the direction of the excavation. And we want to have a bending moment, which is 20 kilonewton meter. Yes, so here are the loads. And when we go back, the safety factors are filled out automatically, yeah, based on the chosen standard. So yeah, say when it's a live load, it's like 1.5, and the dead load is like 1.35. Yeah. And DC bearing calculates the ground failure just in the X direction, but in both sides then, in this direction or in this direction. And the most unfavorable direction is the relevant one. DC footing instead calculates the bearing capacity for all directions, like also like in the X direction here, or like in the Y direction, which you can see here because we just have the X and the Z axis here. The Y axis is like goes like in the plot then. Yes. Then we can go on to the output. First, you can see all the detailed information about standard, design approach, foundation, dimensions, soil data, load case, partial safety factors. On the second page, we have the detailed information about the verification for the load case 1 for the excavation A1, which we have given. Yeah. Yeah, first we can see the loading here with the characteristic and design values. So we have an imposed load and the self weight, which gives the total load then, like when we add both together. The horizontal load, the moment, and the different loads with like vertical, horizontal, and the bending moment have different influences in the verification. So the resultant load from vertical and horizontal is inclined here. It's calculated here. And the bending moment, like with the bending moment, we have an equivalent width, which is given here. It's the original width, like 3 meters, minus 2 times the eccentricity. And with this equivalent width, the load is applied centrically, like in theory then, and like this width is used in the verification then. Yeah, then we can see the dimensions of the failure feature. You can see this later in the graphic as well. Then we have gamma, phi, and c, which are averaged. And then we have all the coefficients which which are calculated in the program. The inertia coefficient, like based on the angle of friction. Then we have the load inclination effect here with I, and the shape coefficients, like based on the foundation dimensions. Then the ground inclination lambda, and the base inclination. Like we have a base inclination with 5 degrees. Yeah, then we have the bearing capacity, which is shown here, kilonewton per square meters, and then we have the capacity resistance as a design value, and this must be greater than the design value of the loads. And as we can see, the utilization factor is less than 1. It's very small, 0.26, and the verification is fulfilled. Yes. So yeah, here's like one comment about the slope. I will explain this in a graphic then. Yeah. As I mentioned, we have this table now with the different widths, like from 1.5 meters to 4 meters. What we wanted, like with a distance, like a difference always like of 0.25 meters, the equivalent width, and then the resistance and the utilization factor. And we can see now that the utilization factor is close to 1 at a width between 0.75 and 2 meters. So like when we like the foundation could be quite smaller for the given load. So the foundation could be like about like approximately 1.8 meters in width. So yeah, then the utilization factor would be 1-ish. Yeah. Then we move on to the graphic. You can see the ground failure picture here in the picture, and yeah, it goes through all 3 layers as we as I said before. And yes, we like I said, like we have this like really small steep slope here, and the coefficient lambda, like for the ground inclination, just works for like an endless slope. So like this like the lambda is calculated for the slope which like would continue in this direction then. Yeah. But we have a small slope here which ends here. And so what the program does is that it kind of like makes a new slope then. You can see this line here. So this is like it's a parallel line to like the kind of slope which the program calculates with. So the slope would start here, and it would like cut in the middle of the slope here, and like it would cut this part here. It would go over here, and then it would like continue like in the same inclination angle. Yeah. So like this small part and this small part here like would be the same then, and this is like the way how the program calculates a new like endless slope inclination. And like if we would like calculate with this like steep inclination, like lambda would be like really small, and we would have like a very unfavorable result. So yeah, we have like a more a better and more realistic result when we have like this new like inclination. Yes, and as I mentioned before, this the ground failure feature goes in the left direction because we have the excavation on the left side.